Vapor-liquid equilibrium is a condition in which a liquid and its vapor are in equilibrium with each other. A condition or state where the rate of evaporation equals the rate of condensation on a molecular level such that there is no net vapor-liquid interconversion. A substance at vapor-liquid equilibrium is generally referred to as a saturated fluid. For a pure chemical substance, this implies that it is at its boiling point. The notion of saturated fluid includes saturated liquid vapor mixture, and saturated vapor. Although theoretically equilibrium is never reached, equilibrium is practically reached in a relatively closed location if a liquid and its vapor are allowed to stand in contact with each other with no interference or only gradual interference from the outside. However, this does not apply to cases of intensive heat exchange or rapid pressure change. VLE data introduction. The concentration of a vapor in contact with its liquid, especially at equilibrium, is often expressed in terms of vapor pressure, which will be a partial pressure if any other gas are present with the vapor. The equilibrium vapor pressure of a liquid is in general strongly dependent on temperature. At vapor-liquid equilibrium, a liquid with individual components in certain concentrations will have an equilibrium vapor in which the concentrations or partial pressures of the vapor components have certain values depending on all of the liquid component concentrations and the temperature. The converse is also true. If a vapor with components at certain concentrations or partial pressures is in vapor-liquid equilibrium with its liquid, then the component concentrations in the liquid will be determined dependent on the vapor concentrations and on the temperature. The equilibrium concentration of each component in the liquid phase is often different from its concentration in the vapor phase, but there is a relationship. The VLE concentration data can be determined experimentally, or computed or approximated with the help of theories such as Raoult's law, Dalton's law, and Henry's law. Such VLE information is useful in designing columns for distillation, especially fractional distillation, which is a particular specialty of chemical engineers. Distillation is a process used to separate or partially separate components in a mixture by boiling followed by condensation. Distillation takes advantage of differences in concentrations of components in the liquid and vapor phases. In mixtures containing two or more components, the concentrations of each component are often expressed as mole fractions. The mole fraction of a given component of a mixture in a particular phase is the number of moles of that component in that phase divided by the total number of moles of all components in that phase. Binary mixtures are those having two components. Three-component mixtures are called ternary mixtures. There can be VLE data for mixtures with even more components, but such data is often hard to show graphically. VLE data is a function of the total pressure, such as 1 atmosphere or whatever pressure the process is conducted at. When a temperature is reached such that the sum of the equilibrium vapor pressures of the liquid components becomes equal to the total pressure of the system, then vapor bubbles generated from the liquid begin to displace the gas that was maintaining the overall pressure, and the mixture is said to boil. This temperature is called the boiling point of the liquid mixture at the given pressure. The boiling point at an overall pressure of 1 atmosphere is called the normal boiling point of the liquid mixture. Thermodynamic description of vapor-liquid equilibrium. The field of thermodynamics describes when vapor-liquid equilibrium is possible, and its properties. Much of the analysis depends on whether the vapor and liquid consist of a single component, or if they are mixtures. Pure systems if the liquid and vapor are pure, in that they consist of only one molecular component and no impurities. Then the equilibrium state between the two phases is described by the following equations. And where under the pressures within the liquid and vapor, under the temperatures within the liquid and vapor, and another molar Gibbs free energies within the liquid and vapor, respectively. In other words, the temperature, pressure and molar Gibbs free energy are the same between the two phases when they are at equilibrium. An equivalent, more common way to express the vapor-liquid equilibrium condition in a pure system is by using the concept of Fugacity. Under this view, equilibrium is described by the following equation, wherein are the fugacities of the liquid and vapor, respectively, at the system temperature T's and pressure P's. Using fugacity is often more convenient for calculation, given that the fugacity of the liquid is, to a good approximation, pressure independent, and it is often convenient to use the quantity, the dimensionless fugacity coefficient, which is 1 for an ideal gas. Multi-component systems. In a multi-component system, where the vapor and liquid consist of more than one type of molecule, describing the equilibrium state is more complicated. For all components I in the system, the equilibrium state between the two phases is described by the following equations, and where P and T are the temperature and pressure for each phase, and another partial molar Gibbs free energy, also called chemical potential, within the liquid and vapor, respectively, for each phase. The partial molar Gibbs free energy is defined by, where G is the Gibbs free energy, and N is the amount of substance of component I. Boiling point diagrams. Binary mixture VLE data at a certain overall pressure, such as 1 atmosphere, showing mole fraction vapor and liquid concentrations when boiling at various temperatures, can be shown as a two-dimensional graph called a boiling point diagram. The mole fraction of component 1 in the mixture can be represented by the symbol x1. The mole fraction of component 2, represented by x2, is related to x1 in a binary mixture as follows. x1 plus x2 equals 1 in multi-component mixtures in general with n components. This becomes x1 plus x2 plus xn equals 1. The preceding equilibrium equations are typically applied for each phase individually, but the result can be plotted in a single diagram. In a binary boiling point diagram, temperature is graphed versus x1. At any given temperature where both phases are present, vapor with a certain mole fraction is in equilibrium with liquid with a certain mole fraction. The two mole fractions often differ. These vapor and liquid mole fractions are represented by 2 points on the same horizontal isotherm line. When an entire range of temperatures versus vapor and liquid mole fractions is graphed, two lines result. The lower one, representing the mole fraction of the boiling liquid at various temperatures, is called the bubble point curve. The upper one, representing the mole fraction of the vapor at various temperatures, is called the dew point curve. These two lines necessarily meet where the mixture becomes purely one component, namely where x1 equals 0 or x1 equals 1. The temperatures at those 2 points correspond to the boiling points of each of the two pure components. For certain pairs of substances, the two curves also coincide at some point strictly between x1 equals 0 and x1 equals 1. When they meet tangentially. The dew point temperature always lies above the boiling point temperature for a given composition when they are not equal. The meeting point is called an azeotrope for that particular pair of substances. It is characterized by an azeotrope temperature and an azeotropic composition, often expressed as a mole fraction. There can be maximum boiling azeotropes, where the azeotrope temperature is at a maximum in the boiling curves, or minimum boiling azeotropes, where the azeotrope temperature is at a minimum in the boiling curves. If one wants to represent a VLE data for a three-component mixture as a boiling point diagram, a three-dimensional graph can be used. Two of the dimensions would be used to represent the composition mole fractions, and the third dimension would be the temperature. Using 2 dimensions, the composition can be represented as an equilateral triangle in which each corner representing one of the pure components. The edges of the triangle represent a mixture of the two components at each end of the edge. Any point inside the triangle represent the composition of a mixture of all three components. The mole fraction of each component would correspond to where a point lies along a line starting at that component's corner and perpendicular to the opposite edge. The bubble point and dew point data would become curved surfaces inside a triangular prism, which connect the three boiling points on the vertical temperature axis. Each face of this triangular prism would represent a two-dimensional boiling point diagram for the corresponding binary mixture. Due to their three-dimensional complexity, such boiling point diagrams are rarely seen. Alternatively, the three-dimensional curved surfaces can be represented on a two-dimensional graph by the use of curved isotherm lines at graduated intervals, similar to iso-altitude lines on a map. Two sets of such isotherm lines are needed on such a two-dimensional graph. One set for the bubble point surface and another set for the dew point surface. K values and relative volatility values the tendency of a given chemical species to partition itself preferentially between liquid and vapor phases, is the Henry's law constant. There can be VLE data for mixtures of 4 or more components, but such a boiling point diagram is hard to show in either tabular or graphical form. For such multi-component mixtures, as well as binary mixtures, the vapor-liquid equilibrium data are represented in terms of K values defined by where Y and X the mole fractions of component I and the phases Y and X respectively. For Raoult's law, for modified Raoult's law, where is the activity coefficient, pi is the partial pressure and P is the pressure, the values of the ratio K are correlated empirically or theoretically in terms of temperature, pressure and phase compositions in the form of equations, tables or graphs such as the de Priester charts. For binary mixtures, the ratio of the K values for the two components is called the relative volatility, denoted by alpha, which is a measure of the relative ease or difficulty of separating the two components. Large-scale industrial distillation is rarely undertaken if the relative volatility is less than 1.05, with the volatile component being I and the less volatile component being J. K values are widely used in the design calculations of continuous distillation columns for distilling multi-component mixtures. Vapor-liquid equilibrium diagrams. For each component in a binary mixture, one could make a vapor-liquid equilibrium diagram. Such a diagram would graph liquid mole fraction on a horizontal axis and vapor mole fraction on a vertical axis. In such VLE diagrams, liquid mole fractions for components 1 and 2 can be represented as x1 and x2 respectively, and vapor mole fractions of the corresponding components are commonly represented as y1 and y2. Similarly, for binary mixtures in these VLE diagrams, x1 plus x2 equals 1 and y1 plus y2 equals 1. Such VLE diagrams are square with a diagonal line running from the corner to the corner for reference. These types of VLE diagrams are used in the McCabe-Thiele method to determine the number of equilibrium stages needed to distill her given composition. Binary feed mixture into one distillate fraction and one bottoms fraction. Corrections can also be made to take into account the incomplete efficiency of each tray in a distillation column when compared to a theoretical plate. Raoult's law. At boiling and higher temperatures, the sum of the individual component partial pressures becomes equal to the overall pressure, which can be symbolized as PTOT. Under such conditions, Dalton's law would be in effect as follows: PTOT equals P1 plus P2 plus. Then for each component in the vapor phase, Y1 equals P1 PTOT, Y2 equals P2 PTOT, etc., where P1 equals partial pressure of component 1, P2 equals partial pressure of component 2, etc. Raoult's law is approximately valid for mixtures of components between which there is very little interaction other than the effect of dilution by the other components. Examples of such mixtures include mixtures of alkanes, which are nonpolar, relatively inert compounds in many ways, so there is little attraction or repulsion between the molecules. Raoult's law states that for components 1, 2, etc., in a mixture, P1 equals X1 PO1, P2 equals X2 PO2, etc., where PO1, PO2, etc., are the vapor pressures of components 1, 2, etc., when they are pure, and X1, X2, etc., are mole fractions of the corresponding component in the liquid. Recall from the first section that vapor pressures of liquids are very dependent on temperature. Thus the pure vapor pressures for each component are a function of temperature. For example, commonly for a pure liquid component, the Clausius-Clapeyron relation may be used to approximate how the vapor pressure varies as a function of temperature. This makes each of the partial pressures dependent on temperature also regardless of whether Raoult's law applies or not. When Raoult's law is valid, these expressions become P1T equals X1 PO1T, P2T equals X2 PO2T, etc. At boiling temperatures, if Raoult's law applies, the total pressure becomes PTOT equals X1 PO1T plus X2 PO2T plus, etc. At a given PTOT, such as 1 atmosphere and a given liquid composition, T can be solved for to give the liquid mixture's boiling point or bubble point, although the solution for T may not be mathematically analytical. For a binary mixture at a given PTOT, the bubble point T can become a function of X1, and this function can be shown on a two-dimensional graph like a binary boiling point diagram. At boiling temperatures, if Raoult's law applies, a number of the preceding equations in this section can be combined to give the following expressions for vapor mole fractions as a function of liquid mole fractions and temperature. Y1 equals X1 PO1T, PTOT, Y2 equals X2 PO2T, PTOT, etc. Once the bubble point T's as a function of liquid composition in terms of mole fractions have been determined, these values can be inserted into the above equations to obtain corresponding vapor compositions in terms of mole fractions. When this is finished over a complete range of liquid mole fractions and their corresponding temperatures, one effectively obtains a temperature T function of vapor composition mole fractions. This function effectively acts as the dew point T function of vapor composition. In the case of a binary mixture, X2 equals 1 minus X1, and the above equations can be expressed as Y1 equals X1 PO1T, PTOT, and Y2 equals PO2T, PTOT for many kinds of mixtures, particularly where there is interaction between components beyond simply the effects of dilution. Raoult's law does not work well for determining the shapes of the curves in the boiling point or VLE diagrams. Even in such mixtures, there are usually still differences in the vapor and liquid equilibrium concentrations at most points, and distillation is often still useful for separating components at least partially. For such mixtures, empirical data is typically used in determining such boiling point and VLE diagrams. Chemical engineers have done a significant amount of research trying to develop equations for correlating and/or predicting VLE data for various kinds of mixtures which do not obey Raoult's law well.